Here is a result that should make you pause. In this dataset of children, smokers appear to have better pulmonary function than non-smokers. Pulmonary function is measured using forced expiratory volume in 1 second, or FEV₁, which reflects the amount of air a child can forcefully exhale in the first second after a deep breath. Lower values of FEV₁, relative to expected values for age, sex, and height, indicate impaired respiratory function, and smoking status was collected by self-report. This leads to a simple question. On average, among these children, does FEV₁ differ between smokers and non-smokers? A natural starting point is the two-sample t-test, since we are comparing a continuous outcome between two groups. The results suggest that smokers have a higher mean FEV₁ than non-smokers, with a difference of about 0.71 liters, with a 95% confidence interval from 0.50 to 0.92, and a p-value less than 0.001. Based on this analysis alone, smokers appear to have better pulmonary function. This conclusion is unexpected and suggests that the comparison may be misleading. From a statistical standpoint, the setup seems appropriate, but statistical validity does not guarantee scientific validity. When results contradict established knowledge, the issue often lies in how the comparison was constructed. This is the focus of this video: how a simple comparison can lead to the wrong conclusion, and how to think more carefully about what we are seeing. If a simple comparison suggests smokers have higher FEV₁, what might be going wrong? Think you know the answer? Take the quiz at the end of the video. I'm Jose B., the traveling medical data scientist. In this video, we use a common tool, the two-sample t-test, to compare two groups. Although widely used, this method can produce misleading conclusions when the comparison is poorly constructed. We'll see how this happens and how to correct it. Our biggest enemy in research is bias. Bias occurs when the comparison we make does not reflect the true relationship we are trying to study. It can produce results that are statistically significant and look convincing, yet lead to completely incorrect conclusions. This dataset includes 654 youths aged 3 to 19 years from the Childhood Respiratory Disease Study in East Boston. The wide age range is critical. This dataset was later included in Bernard Rosner's textbook, Fundamentals of Biostatistics. Some observers focus on the p-value, but a p-value without data visualization and numerical summaries is like a building without a foundation. Exploratory data analysis often feels like just looking, but that is exactly what prevents conclusions as absurd as smoking improves lung function. The problem is not the mathematics, but the uncritical trust placed in it. Before trying to explain this apparent paradox, we need to examine the data more carefully using both visual displays and numerical summaries. Rather than treating all individuals as a single group, we divide the data into more comparable groups based on age. Two patterns emerge. First, FEV₁ increases with age. Second, the age distributions differ. Non-smokers span a broad age range, while smokers are concentrated among older teenagers. Overall, smokers are generally older than non-smokers. In other words, age is associated with both the exposure and the outcome. Smokers are disproportionately older, so the smoking group contains more older children. Because lung capacity increases with age, older children naturally have higher FEV₁. As a result, the combined data can make smoking appear beneficial when the difference is actually driven by age. We can assess the role of age by comparing crude and age-adjusted estimates. Once we account for age and compare children within the same age groups, the pattern changes. In the 3 to 8 group, there are no smokers, so no comparison can be made. In the 9 to 11 group, smokers have slightly higher FEV₁ than non-smokers. In the 12 to 14 group, smokers have slightly lower FEV₁. In the oldest group, smokers have substantially lower FEV₁ than non-smokers. The direction of the association is not consistent across age groups. This reversal occurs because smokers in this dataset tend to be older, and older children naturally have higher lung function. When we examine each age group separately, the apparent advantage of smokers disappears, and in the older groups, it reverses. When we ignore age and combine all observations, smokers appear to have higher mean FEV₁. This apparent difference does not reflect a true association between smoking and FEV₁. Instead, it is driven by differences in age between the groups. This is Simpson's paradox, where a pattern observed in the combined data disappears or reverses after stratifying into more comparable groups. The key takeaway is simple. The apparent association may be driven not by smoking, but by differences in age between smokers and non-smokers. We also observe that the association between smoking and FEV₁ differs across age groups. Smoking is associated with slightly higher FEV₁ in younger children, but lower FEV₁ in older children, with the largest difference in the 15 to 19 group. Taken together, the association between smoking and FEV₁ is not constant, but depends on age. There are two equivalent ways to describe this. In statistical terms, age interacts with smoking in their association with FEV₁. In epidemiologic terms, age modifies the association between smoking and FEV₁. Because we are defining the contrast using differences in means, that is, on an additive scale, interaction and effect modification refer to the same concept. In other fields, this is called moderation. Because older children are more likely to smoke and also have higher FEV₁, smokers and non-smokers are not comparable in terms of age, so a single overall comparison is no longer sufficient. The concept of statistical interaction, or epidemiologic effect modification, is actually familiar to most of us. For example, we know that patients taking an ACE inhibitor such as lisinopril should avoid NSAIDs such as Advil, because there is a drug interaction between Advil and lisinopril. This interaction means that Advil can interfere with lisinopril's ability to lower blood pressure. In other words, Advil modifies the effect of lisinopril on blood pressure reduction. If the answer is, it depends, that suggests the presence of interaction, meaning the effect of X on Y varies across levels of another variable. So far, we have used a conceptual diagram to illustrate interaction, showing how the relationship between smoking and FEV₁ depends on age. That diagram captures the structure, but not how it appears in the data. We now turn to a standard interaction plot, comparing mean FEV₁ between smokers and non-smokers within each age group. Among children aged 9 to 11, smokers have a higher mean FEV₁, with a difference of about 0.33 liters, with a p-value of 0.08. Among children aged 12 to 14, non-smokers have a slightly higher mean FEV₁, with a difference of about 0.09 liters, with a p-value of 0.61. In the oldest group, ages 15 to 19, smokers have lower mean FEV₁ by about 0.61 liters, with a p-value of 0.01. Because 3 comparisons were performed, a Bonferroni adjustment sets the significance level to approximately 0.02. Under this threshold, the difference in the oldest group remains statistically significant. Notice that the lines are not parallel. This indicates that the association between smoking and FEV₁ varies across age groups, and in fact reverses direction. This is a clear example of interaction. More formally, we can fit a two-way ANOVA model with smoking status and age group as factors, excluding the youngest group since there are no smokers. The p-value for the interaction term is 0.002, providing statistical evidence of interaction. Having established interaction, we conclude that the association between smoking and FEV₁ varies across age groups. Interaction and confounding address different issues. Interaction describes how the association differs across age groups, whereas confounding concerns the comparability of groups. In practice, interaction is assessed first because it determines whether a single overall effect is meaningful. If the effect varies across age groups, confounding by age is controlled through stratification, and comparisons should be made within age groups. Within each stratum, however, there may still be confounding by other covariates, which should be evaluated and, if necessary, controlled. The crude overall estimate is plus 0.71 liters. This estimate is inconsistent with the age-specific effects, a discrepancy that arises because smokers and non-smokers are not similarly distributed across age groups. Because interaction between smoking and age is present, the appropriate approach is to report age-specific effects rather than a single overall estimate. Within each age stratum, comparisons are made among individuals of similar age, so confounding by age is substantially reduced. As a result, stratum-specific estimates largely account for age differences. However, some residual confounding by age may remain, and confounding by other variables may still be present within each stratum and should be considered. Returning to the original question, is smoking associated with pulmonary function in children? The answer is, it depends on age. Among children aged 9 to 11 years, smokers have a higher mean FEV₁, although the difference is not statistically significant. Among those aged 12 to 14 years, there is little difference between groups. In contrast, among adolescents aged 15 to 19 years, smokers have lower mean FEV₁, and this difference is statistically significant, even after Bonferroni adjustment. Overall, the association between smoking and FEV₁ varies by age, with evidence of a negative association only among older adolescents. When age is treated as a categorical variable, information is lost and arbitrary cut points are imposed. This can reduce statistical power and obscure patterns that vary smoothly across age. To address this, we use regression modeling, treating age as a continuous variable and including an interaction term between age and smoking. The model expresses FEV₁ as a function of smoking, age centered at 12 years, and their interaction. The interaction term is negative and statistically significant. This indicates that the difference in mean FEV₁ between smokers and non-smokers becomes more negative with increasing age. This result is consistent with the pattern observed when age was modeled as a 4-level categorical variable, but the regression approach additionally quantifies how this difference varies across age. Now for today's takeaways. When we ask whether an exposure is associated with an outcome, we often expect a single summary estimate. In this case, however, the association between smoking and FEV₁ varies across age. Because the association between smoking and FEV₁ varies by age, it cannot be summarized by a single overall effect, as in a 2-sample t-test. Instead, the data should be stratified by age, and age-specific associations should be reported. Comparing smokers and non-smokers within each age group involves individuals of more similar ages, which reduces confounding by age. However, confounding by other variables may still be present. Smoking seems to boost FEV₁ in children at first glance, but once age enters the picture, the story flips on its head. Are you ready for today's quiz? An observational analysis compares mean follow-up systolic blood pressure between patients receiving lisinopril in addition to standard hypertension care, and those receiving standard care without lisinopril using a 2-sample t-test. The Crude analysis suggests that patients receiving lisinopril have higher follow-up blood pressure, but those patients also started with more severe hypertension. The analyst then stratified patients into mild, moderate, and severe baseline hypertension groups and compared them within each stratum. Given this, why was a 2-sample t-test comparing the 2 treatment groups inappropriate? In other words, why was stratification necessary? Feel free to pause the video if you need more time to think about the question. The correct answer is D. Baseline systolic blood pressure is associated with both treatment and the outcome. Patients with more severe hypertension are more likely to receive lisinopril and also tend to have higher follow-up blood pressure. Without stratification, the comparison is distorted because the groups are not comparable. Are you ready for another question? A randomized controlled trial by Marler and colleagues, published in the New England Journal of Medicine, evaluated alteplase versus placebo among patients treated within 3 hours of stroke onset. Within this treatment window, the effect of alteplase on stroke outcome varied by time to treatment. Outcomes differed between patients treated within 0 to 90 minutes and those treated within 91 to 180 minutes, with greater benefit at earlier treatment times. Given this interaction, how should the results be reported? Feel free to pause the video if you need time to think through your answer. The correct answer is C. The study shows that the effect of alteplase varies by time to treatment, specifically between 0 to 90 minutes and 91 to 180 minutes. Because the treatment effect differs across these intervals, a single overall estimate would obscure this variation. Adjusting for time does not resolve this issue, because it assumes a single underlying effect. Instead, the results should be reported separately within each time interval, making the difference in treatment effect explicit. As the title of this channel suggests, I'm a traveling medical data scientist. Today, I'm sharing footage I captured in the mountains of La Paz, Honduras. I didn't find this place in a guidebook. In fact, many people in Honduras haven't heard of it. I learned about it through a conversation with someone I met along the way who mentioned a hidden waterfall deep in the mountains. There were no roads to get there. We had to cut through dense vegetation with a machete, and I wore boots because of the risk of venomous snakes hidden in the grass. The climb was not easy, but when I finally reached the waterfall, it was worth it. I can't be certain, but I'd like to think this may be the first time this place has been captured on drone footage. After spending time with a local community, I realized this is one of the country's hidden treasures. I'm grateful to the people who guided me there and shared their version of paradise. That's all for today. Thanks for watching. This is Jose B., the traveling medical data scientist, signing off.